Cool. All right. Welcome, everybody. Today is a beautiful, sunny, special day because I didn't have to prepare any lecture notes. And we have a guest, Yaron Minsky from Jane Street Capital. So I mentioned Jane Street and the work that they do with Camel at the beginning of the year. I hope you remember some of that if you go back and look at the notes. Yaron's going to come and talk to you about what I think is probably the shop of programmers that knows the deepest and most about Camel, except maybe the guys in France who made Camel itself.
Those guys are pretty good.
They're good, yeah. Do we have any announcements, Victor, for class? No? Okay. I hope you're working on your projects, making lots of progress on that. Yeah, good? Okay. Yaron, let's see, I forgot where you did your undergraduate work, but I know where he did his graduate work because I was there. It was at Cornell. He was actually a distributed systems guy. He's not a programming language person. So this is why it's doubly good to bring him in as far as I'm concerned, because he came to ML as a skeptical systems guy, but he hung out with some PL people who helped convince him ultimately. So Yaron, welcome, and please take it away.
I think I was actually convinced by the other system guys who had themselves already been converted in the department. So I actually knew that Greg had given Jane Street a mention earlier in the semester because I looked at the online version of this course, and the first few lectures are up online. And I was dismayed to discover when I watched the lectures, to sort of remember the thing that I had already known when I knew Greg back at Cornell, that he is sadly a good lecturer. So normally when I come in to speak to a set of undergraduates at a university, I feel secure in the knowledge that the normal lectures they get are terrible. And so, therefore, my lecture will look better by comparison. But sadly, there's good competition here. So the talk I want to give is about effective ML. And I've stolen the title of the talk from a book I really like about Java by a guy named Joshua Block, who is, I think, the chief Java architect at Google or something like that. A guy who used to be at Sun, who wrote a book called Effective Java, which is, for my money, the best book about programming in Java that I've ever looked at. And in fact, many years ago when I first got to Jane Street and I wanted to help out and give people advice about how to program effectively, the thing I did was I went out and bought a bunch of copies of Josh's book and handed them out to people. So now, after having programmed for about 8 years, off in the real world in industry using ML, I've sort of come up with some of my own ideas about how to program effectively in ML. And most of so the talk is going to be broken up into two parts. And I've never given this talk before, so I don't really know how far I'll get. The first thing I want to do is, in the kind of style of Effective Java, that book is broken up into a number of small observations about how to program well in Java. And so I want to do something similar, go through a series of small observations about how to program well in ML. And then I want to talk about a couple of bigger issues, kind of larger scale issues about how to deal with a large ML code base in the real world. So every talk comes from a point of view, and this one is no different. So I wanted to spend a little bit of time talking about the point of view that this talk comes from. And that point of view is the point of view of the kind of work that we do. So I want to give a kind of very brief overview of what Jane Street does, and more importantly, what kind of programming environment we have, what kind of problems we solve, and what our constraints are. So Jane Street itself is what's called a proprietary trading company. The basic thing that the company does is they're kind of electronic market makers, liquidity providers, people who basically serve the same role that the guy who runs a grocery store serves, who sits in the middle between the people who want to buy things and the people who want to sell things, makes a little money on every transaction, does lots of volume, makes a small amount for each transaction, and thereby earns his keep. That's the kind of broad business that we belong to, and one of the results of that is we do a lot of volume, right? How do you make up for those really thin margins? You make it up on volume. So we do an enormous amount of trading. There's billions of dollars of nominal value kind of sloshing back and forth in the systems that we build. And what this means is that we are very nervous about technological risk, because there's no faster way to light yourself on fire than to write a piece of software that makes the same bad decision over and over in a tight loop. And as you make your systems faster and more effective and you increase your scope, you also increase the likelihood that you will incinerate yourself. So we are very careful about correctness of code. That's a kind of key kind of motivator of the way that we approach things. And I think unusually, the primary way that we think about correctness, that we try and get to correctness, is via trying to write code that is understandable and having strong practices of reading that code. So I think every software shop out there spends some amount of effort reading code and some amount of effort testing code. But just as many people talk about test-driven development, I think if anything, we're more like code review-driven development. We think a lot about the point of view of the person who reads the code. And the reason for that is, in a kind of financial setting, it's not the everyday condition that matters. It's the weird thing that happens off in the tail of the distribution that doesn't happen very often, so it's hard to test for, but happens more often than you would have thought if you sort of imagined everything was a nice, fast decreasing normal distribution, because financial distributions throw up unusual events more often than you would think. And some of these things are hard to test for, and so we really want to have code that we really deeply understand, not just understand how it normally behaves, but also understand its internals, understand the intent behind it. And so we kind of, as a company, view code not just as a way of getting things done, but also as a means of expression, right? A way of saying what the system is supposed to do. Now, this shouldn't lead you to think that, that we only do this kind of correctness critical stuff. Like sometimes you can go and read a paper about how NASA develops software. And they do all this crazy stuff to make absolutely sure, or almost absolutely sure, that nothing goes wrong in the rockets because it's so expensive to get things wrong. And then you think, that's really cool, but I'm not going to build my web crawler that way because I don't care, right? It's like if there's a 1 in a million chance that something horrible happens, like it's just not that big of a deal. And it's worth noting that not all of the work we do, not all of the code we write is correctness critical. A lot of it has other more important things for it are things like speed to delivery. We do a lot of research coding. So we write our own research software, and there prototyping has a really big value. We write software for doing systems administration in ML. And again, like it's important that those things be correct, but there are so many sources of errors in your average operating system install that making sure things are correct there is more about layering lots of different kinds of independent checks than it is about building one really, really solid executable. So there's a fairly wide diversity of different kinds of things that we do. One thing that is really different about our kind of shop from many shops is that we don't integrate with a lot of outside code. There are some kinds of things that we integrate with, like everyone else, but we don't do a lot of building of web UIs or GUI toolkits or joining into 16 different proprietary databases. Like most of the stuff we do is bespoke. We build our own stuff, and we have all the code, and we can change everything, right? And I think that that's very different. Like other software development shops often have to worry a lot more about the code that they can't modify and how to deal with that. And that's mostly a problem that we don't have. Another difference about us ties to something which I think has bedeviled people who care about programming languages like ML for a long time, which is the question of why the hell doesn't the language catch on, right? People who like ML think it's wonderful, think it's the best approach to building software, or at least one of the best approaches to building software. And yet it is hilariously unpopular, right? Nobody uses these languages. They're a very, very small minority of programmers in the world who've even heard of languages like ML. And the question is why? And one of the theories is that maybe these languages are kind of too hard for the average programmer. And I don't really know if this is true. Like there are kind of reasons to think it is, reasons to think it isn't. But one of the privileges of working at a place like Jane Street is the reaction that we have to the average programmer is not to hire them, right? So we don't have to worry about the question of like, are these techniques too hard for someone who doesn't have a very good background in computer science to understand? We can focus on making people who do have a very strong background more effective. So that's kind of what I wanted to say about the kind of background of the firm. now let me get to kind of the core lessons that I want to talk about. So I'm just going to go through one by one a set of kind of small ideas, and I'll bring up some code to demonstrate these ideas. And the first one I want to talk about is kind of a meta idea. And this goes back to what I said about how we do a lot of reading of code. And one of the things I've noticed over the last 8 years is that, well, there are some people who work for us who spend a lot of their time, in fact, spend most of their time writing code. And there are some people who spend a significant fraction also reading the code of others. And there are systematic differences in opinion between the people who mostly write code and the people who spend lots of time reading code. And I used to be a guy who mostly wrote code. And then as more people came on, I switched more to being a guy who mostly reads code. And one of the things I realized over time was that whenever there's a difference of opinion between these two groups, and there often is, the readers are always right and the writers are always wrong, right? And the reason for this is that at least this is the case if you're building something that's going to last, that multiple people are going to use, that's going to be shared. Because the interest of the reader always pushes in the direction of clarity, simplicity, and moreover, that's kind of the ability to change the code later. Right? And that's actually another thing I didn't mention, which is also very important in the kind of work that we do, is that we do lots of building of new systems, and we do an enormous amount of changing of existing systems. Building software systems that can evolve effectively and maintain correctness under that evolution is essential. And so whenever you see a trade-off between, what would you like to do if you were the guy writing the code, and what would you like to do if you were the guy who was forced to read the code, you should always err in the direction of the reader. Right? At least, as I said, at least if the code, if it's a throwaway thing that you're going to write a script and throw it away, maybe it doesn't matter because there won't be any readers. But in most real projects, code is read and changed many more times than it is written. And so the reader's interests are paramount in that regard. So now to something a little bit more concrete, creating uniform interfaces. So in OCaml, there's a thing called an MLI, which is this interface file which constrains the interface of the module that you write. So actually, this is a 2-for-1. There are two pieces of advice here. One is create interfaces. And again, this is one of these things between readers and writers. Like all the code I wrote at first, I was like, interfaces. I'll write 80,000 lines of code and not put any interfaces anywhere because I know what I'm doing, right? And this, it turns out after a while, someone else has to read some of the code that you wrote. And the worst case scenario is when the jerk who's reading the code, who doesn't understand what you did, is you, right? Because it's some time later and you've forgotten some details. And you don't know what you meant back 6 months ago when you wrote that. And boy, are you mad. Today you is really mad at that old guy. So even though it's tempting not to, if the project is expected to have any longevity, you should write interfaces. And when you write interfaces, you should create uniform interfaces. You should have standards about how interfaces should be built and apply those standards uniformly to the code base. And again, this is something, you're writing a project for yourself, no one else is going to use, not as big of a deal. You're writing a project which you have 40 people who are going to be collaborating on. It's really important because having these uniform interfaces gives solid expectations that someone can take in to some new piece of code and use to quickly navigate and understand. It greatly increases the kind of sort of flexibility and speed of people who are interacting with your code base. By the way, I should stop myself to say I am prone to going too fast, and people should feel very free to ask questions. I'm about to do the horrible thing of throwing code on the board, and half the class is going to be confused about it, and no one will raise their hand, and then they'll just stay confused. So don't do that. Ask actual questions. One thing what I want to pull up now is an example of a technique that we use for enforcing uniform interfaces. And this is basically, what we basically do is we have interface components. So we write module signatures. So if you look up there at the top line, it says module type comparable. So that declaration module type is basically the same thing as, it's very similar to the declaring what's in an MLI, right? It's declaring this a signature. Here it's but here, unlike in MLI, where the MLI is kind of married to a particular implementation, this is a freestanding signature. And the idea is that this signature sums up what it means for something to be comparable, for some type to support a comparison operation. And if you see, so there's 3 stanzas in here. The first stanza is a bunch of infix operators. The second stanza is a set of utility functions. The most important one being the original compare one, which sort of sums up the basic ability to compare 2 things. And then the last 2 are actually module interfaces. So these are now submodules. So anything which is comparable has a submodule called map and another submodule called set, which use that comparison operator as the basis of a map type and a set type. And then, so you can have one of these interfaces and then you can use it. So here's an example of using multiple of these interfaces. The way it works is you say module car, so here :sig. So now this really is like an MLI, right? The sig to end is exactly like sticking an MLI on top of an ML file. And so I declared there's a type T, and then I just say include comparable, and then there's a little bit of crupt with type comparable equals T. This is how I kind of force the types to unify in a clean way. It's actually an unfortunate misfeature of OCaml that I need this extra little bit of verbiage to kind of unify the types away. And it's actually something that hopefully is going to be fixed in the next few revisions of the language to make this process a little bit smoother. But it's a little bit of extra boilerplate, but you can basically do it. And then you have these standardized interface components, and there are 2 big wins from this. One of them is that it enforces standards. It's better than just telling people who work there, it's like, you really should follow this interface. It's like, no, you should just include this interface component. And then if you don't follow the interface, your code won't compile, right? There's no better motivator than your code won't compile. And then the other thing is that this makes it much easier to use functors. So have functors been covered at all in this class? Right, so the sort of very short, high-level description of functors is functors are functions from modules to modules, right? And when you have one of these functions, you kind of have to say in the signature of the function, what are you requiring of the input modules? And also, what are you going to give on the output modules? You need to be able to specify the type signature. And you can use these same interface components when you're describing the thing that you expect from the module. And now, everyone who has sort of fulfilled the obligation of satisfying these interfaces can also automatically work along with that functor. And so the fact that everyone follows the same patterns means that functors are much more broadly applicable with less work. Like otherwise, you have to do some sort of horrible, like, rejiggering of the module, like create a new module and pack things in just the right pattern to fit the functor if things don't exactly match. And when you follow these standards, you have to do that a lot less. And for what it's worth, shake there. For what it's worth, when you see this map and set modules, in practice, those are actually created themselves by functors. So that you don't have to actually redo the work of rewriting the map and set module every time you need it. You can create it in an automated way. All right, so uniform interfaces. Here's another, this is a really important one. Make illegal states unrepresentable. What the hell does that mean? What that means is, basically, the key benefit you get, well, there are a number of benefits, but one of the key benefits you get from a language like ML is that the type system basically makes sure that various aspects of your program work properly with a fairly small amount of effort from you. But the type system is not so wonderful that you can't defeat it, right? It turns out you can write your code badly in such a way that the type system doesn't give you very good guarantees. There's a kind of self-fulfilling prophecy that people who come to ML from other languages have, which they say, oh, well, all this really does is make sure that, like, it's an int when I wanted an int. And then they write their code that way. And indeed, then all it does is make sure that you passed in an int where you wanted an int. But anyone who becomes a halfway decent ML programmer has to learn to use the type system as a tool to enforce invariance, to enforce guarantees on the code that they write. And one of the key steps in doing that is choosing your data types in a way that whenever you can, whenever it's practical, that states that don't make sense, that are illegal, don't actually show up as legal states in your program. So let me, again, bring up an example here. So here is a little type definition for an imaginary module for managing the state of a connection. So there are 2 types here to look at. The first one is a variant type. In fact, it's a simple enumerated type, right? There's nothing inside the variance, which just write down the kind of 3 states that a connection can be in: connecting, connected, and disconnected. And then we have this record which is going to include the connection state as a subcomponent, called connection info. And connection info kind of keeps track of all, sort of has a record of all the information that you keep about the state of the connection. And there's a number of pieces here. You have the state, which just points back to that connection state type. There's the server, which is the identity of the server that the connection is connecting to. There's the last ping time and the last ping ID. And the idea here is that in various protocols, you have occasional pings that get sent out as a kind of keep alive mechanism. And here's where you store the last time that you got a ping and the last ID that you got the ID of the last ping you received. Then there's a session ID, which is some identifier that's created when a new session is constructed. And then 2 times, when initiated, which has to do with when you started trying to connect. And again, this is for managing timeouts. The idea being if you started trying to connect and it's taking forever, you might want to give up and disconnect. And then when disconnected, so that if the connection gets terminated for some reason, as can happen for all sorts of exciting reasons, you keep track of the time that that happened. So there's some good things to say about this. So first of all, it keeps track of a bunch of relevant information, which is nice. It's fairly readable. It's interesting that there's a lot of option types here, right? A lot of values that might be filled in and might not be filled in. Now, you don't have to do that. If you were a working language like Java, you wouldn't do that. You would just probably have them as nullable. It's going to keep on biting me. You would have them as nullable values. So you sort of stuff them in there, but maybe they'd be there and maybe they wouldn't. And you could discover by checking carefully, or maybe excitingly at runtime, discover that something that you thought was going to be there wasn't. But this isn't really that much better than the Java version in the sense that there's a bunch of tricky little invariants that kind of need to hold about this data. So for one thing, if you have a last ping time, you should probably also have a last ping ID. And if you don't have a last ping time, you probably shouldn't have a last ping ID. And the session ID, you should really only have if you're connected. And the when initiated, well, only if you're in the process of connecting does it make sense to keep that. And you have to be careful because you might end up, if this is modeling a restartable connection, that when initiated, if you're not careful, might be, you might forget to overwrite it. It might be the when initiated from last time. So you can have real bugs that result from that. And similarly, when disconnected kind of only makes sense when it's been disconnected. And if you've been disconnected, well, you better have it. So there's a bunch of invariants. And there's nothing about this type that helps you at all in enforcing the invariants, right? You sort of look at that and think, oh, every time I create one of these, every time I construct a new one, every time I do a change, I'm going to have to read the code carefully, and I'm going to have a big comment in the front that writes down what the invariants are, and I'm going to have to make sure they all hold, because otherwise I'm going to get this wrong. Right? So what we can do, though, and what I would strongly encourage somebody, if this code showed up at Jane Street, what I would strongly encourage the person to do would be to refactor the types to structure them so that the invariants are just apparent in the types rather than being implicit in the logic surrounding the types. So how do we do that? So here I've now refactored the way this works. So I've kind of turned the structure a little bit inside out. So there's still this connection info type at the bottom, which is a record. But now it only has 2 fields. One is the state, and the other is the server. So can someone tell me why the server is in there, but all the other ones have been kicked out? Can anyone make a guess as to why I've made that design choice? Does it imply anything about the way I'm modeling the connection, that the server's down here rather than up there?
Maybe that it applies to all 3 of the different types up there.
Right.
So therefore it'd be just in the general connection info.
That's right. Basically, the things that I'm putting in here, there's no option by it. It's not like it might be there, it might not be there. It always has to be there, which means whatever state the server is in, whatever state the connection is in, you always know what the server is. Right? And that's exactly what this process is doing. I'm sort of pushing down into the variant the things that depend on which variant you're in. So here we have this, the now connection state is still a variant, but this time it's not a simple enumerated type. It's a variant where the different tags have contents. Right? There's something inside of the constructor. And so when I'm in the connecting state, well, then I have something of type connecting, which is that first record type. When I'm in the connected state, I have something of type connected, similarly with disconnected. And now, if you go look there, what I've done is I've sort of segregated out the values that are relevant to the individual cases. I've done one other thing, by the way. Does anyone, so other than just sort of pushing stuff into the variant, is there another change that people see in the code? There's something else going on in the way I've changed those types.
You fuse together the ping time and the ping ID into a tuple.
That's right. So why do you think? Hold on one second. So why do you think I did that?
So one of them is there, the other one's there too, and vice versa.
Right. And it's worth noting, it's another. Let me fix my damn screen, and then get back. There we go. So the point is, I've stuck them together. So you always have, when you have one, you always have the other. And then the other thing is, it's still optional, right? So it's not like I've gotten rid of all of the variance between the different cases. There's still this one extra possibility that can swing back and forth. But now it's sort of segregated into the right place. And now there are no illegal states. All of the states that can be represented are basically reasonable states, right? And so that's the key way in which this interface is better than the one that we started with. Are there any other questions about this example?
Always do that? Always?
No. The answer is no, you can't always do it, but it is algebraic. So this is the genius of algebraic data types. Like, algebraic data types aren't just like some random idea about how to structure things. There's like a deep kind of mathematical thing going on here, right? You have two basic components, right? You have product types and sum types. Cartesian products and disjoint sums. It's like plus and multiplication. And like, by combining those together in lots of ways, it turns out you can build very complex structures. So you can't do everything, but you can do a lot of things. There are cases where you have to like have invariants written down carefully and have code that carefully checks the invariants every time you go in and out. Like, you don't completely get away from that, but in a surprisingly large variety of cases, you can do it. And I think one of the ways in which variant types are often mispresented in the literature is they often, like, you'll read a book and it'll show you variant types, and it'll do it by showing you how to build a binary tree. And you think, cool, now I can build a binary tree. I never do that, right? I always use a library when I want my map or my fast data structure. So it's like, for this obscure case that I sometimes want to do, now I have this extra tool. But it's just totally wrong. Like, if you couldn't use it for binary trees at all, you'd retain the vast majority of the uses of it. Because what variant types are useful for, by and large, is for kind of the everyday dealing with the fact that, like, you have collections of different things. Damn, I really thought I had that taken care of. The display sleep settings, but it's not the screensaver. All right, I'm going to give up now. Right, and it's that basic, everyday kind of case analysis, which you do in completely vanilla code all the time, that makes variant types such a powerful thing. So, and more importantly, the kind of layered combination of variant and product types, which is what you see here. All right. So this is a closely related idea, which is the idea that one should write your code aiming at exhaustiveness guarantees. So what does this mean? So one of the lovely things that OCaml does is when you use a match statement, there's a simple algorithm that runs that makes sure that the match you have written down is exhaustive, right? And if it's not exhaustive, it warns you. And in fact, the sort of morally correct way to configure your compiler is to have the compiler refuse to compile inexhaustive matches. A warning is not enough. Like, you should not compile code that has inexhaustive matches. And this turns out to be very important because case analysis is a deep, sort of ingrained part of programming. You see it everywhere. And having basic checks, like the fact that your case analysis is exhaustive, is very powerful. And the key thing that sort of, the key benefit you get from it over and over again is as a refactoring tool. As your code evolves, you can use these exhaustiveness checks to figure out where you need to fix things in response to changes in the code base. So, pull up yet another example. So, here's what looks like a kind of, I think, to most people's eyes, a perfectly plausible looking piece of code. So, let me first give a little bit of background on what, on the objects being talked about here. So this is a kind of made-up mini financial example. So the idea is there's this type message which is meant to encapsulate different kinds of messages that you can see in the communication back and forth to, say, an exchange at which you're trading. And there are 3 types of messages described here: an order, a cancel, and an execution. So an order is like when you ask to do something, you ask to buy or sell something. You display your willingness to buy or sell something. A cancel is to state that you no longer want to have that order open. It's like, I'm willing to buy IBM at $33.23. And when you send the cancel for that, you say, no, I'm not. I'm out. I don't want to do that anymore. And then the execution is when you said you were willing to buy something, somebody else said they were willing to sell something, they were at prices where the two could execute against each other, and you got back an execution. And it's when you get back the execution that the world changes. Like, there's an execution, and like now you have more of whatever it is that was in your account, and you have less money because you paid for it, or the other way around if you sold it. And like and the world has changed. And in particular, your position in the security in question, meaning the number of shares you had of it, has changed. So you might want to have a function which takes one of these messages and determines what was the change to your position. So that's what we wrote here. It's called position change. It takes a message M, it matches it. The only case that matters is the exec case, right? So we get that case out. We say if it's an exec, I do a little magic here, which is maybe not so exciting. I do the calculation. I figure out what the position change was, and I return it. And in the other case, I return 0, because those cases have no effect on my position. So this code is lovely. It's correct. There is nothing wrong about it, except that it's not going to do so well when I change the types. In particular, if I go down here and say, you know what? I forgot about one case. There's another thing called a correction. So what's a correction? A correction is where you did a trade on the exchange, and the exchange said, you know what? That wasn't actually the trade you thought it was. We made a mistake. Something bad happened. Actually, you thought you bought 10,000 shares of IBM. Really, you sold 30,000 shares of Vodafone. Good luck. So that particular kind of correction is actually very, very rare, but it does happen. So you get a correction, and now so this code is now wrong, right? Because the correction changes your position, right? It is no longer the case that your position is what it was. But you didn't notice. And the reason you didn't notice is because you had that insidious little underscore there in the last case. You had a catch-all case, which is basically saying, I don't care what else is in the variant. Don't bother me, compiler. I'm sure that I've done all the case analysis I need to do, and I know none of the other cases matter. And that's kind of OK when the world is static. But then when the world is changing, that doesn't work at all. So the right way to have written this code was to have been explicit in the first place about what the cases were. So if you said this in the first place, when you wrote your code, then when the variant message changed, the compiler would have warned you and said, oh, there's a case you didn't think about. Here's the case you didn't think about. Go fix it. And it's hard for me to overemphasize how central this is. Like, every day that I program, I use this, right? It is one of the key things that keeps me sane. Like, you can take lots of other features of the language away from me, but like, with my last dying breath, I will keep my exhaustiveness checks, right? They are, I think, the single best feature of the language. There's kind of automatic checking for what is just a really important part of the everyday kind of part of the pragmatics of programming. Any other questions about the example? OK. So here's another one. Open few modules. So one of the nice features of ML is you can open a module. You can say, you know what, this module has, like, there's a bunch of stuff in this namespace. I want to open up the namespace and be able to access it freely. And it's nice because when you open a module, everything is a little bit shorter. You no longer have to state the name of the module that you're referring to when you want to refer to a value on the inside. And this is great for the guy who wrote the code. But it can be kind of terrible for the guy who has to read the code, because opening a module here and there isn't too bad. But a lot of the time, people will get into the habit of opening like 20 modules, right? And then it's completely insane. Like, you can't keep track of what's going on anymore, because you can't, by looking at the code, have any feel of like where the values came from. So to bring up yet another exciting code example. So here's a complete implementation of the most important Unix utility, true. True is a function that, as the summary down there says, it does nothing successfully. So here I wrote a little implementation of true in OCaml using a library, which you've never seen before, called command. And at the top, I helpfully open command and I open flag. And this is nice because it makes the code a little bit terser. Because if you look over here, these values int and string, these turn out to be special values which are constructors of the flags. It turns out I've gotten a superpowered version of true where I can pass in arguments to make it like print out a value and change its exit code and stuff. So it's like a really featureful. There's like GNU true. It's like an extra powerful version. So, so it's a little bit terser because I wrote it this way. But someone who's reading the code is like int. Where does that come from? Does it come from flag or command or what's that? That core.std. That's opening the standard library. Is this maybe just a utility in the standard library somewhere? Like I have no idea where to go. In fact, where's flag defined? It turns out flag is a submodule of command, right? Although I kind of can't tell that from here. And like this, this isn't too bad. But if you multiply the number of open modules by 20, it's kind of terrible. And you can do better. So here, I've rewritten it, and I took out the opens at the top. And it's actually not that much worse. And one of the reasons it's not that much worse is because I used a couple of little tricks to make it not so bad. And actually the key one is this one over here, where what I did was so command.flag is kind of long. And it would be painful to write command.flag.int and command.flag.string and to do that over and over again, for the 20 different flags to GNU true that I'm going to add later. Right? It's going to be sort of an unpleasant piece of boilerplate if I do that. But with just a little tiny a rename, I can have a nice terse version of the name. And it's important that you do this locally, actually. Like, I could have also done it at the top of the file and said module f equals command.flag at the beginning. But if you imagine this is a big file and you're doing it a lot, what you're doing is you're forcing the guy who's reading the code to remember a lot of things for a long time. And it's important to respect the cognitive limitations of the people who are interacting with the code. Like, people are dumb. They don't have very much memory. Like, you put too many things in their head and the bottom things drop off. If you're going to make them remember something, make them remember it for a short period of time. And that's what this does. We sort of make the definition in one local scope. We use it. And then the guy who's reading knows he can forget about it and never think about it again. And you may have to redo an abbreviation somewhere else. But all told, that kind of approach is a win. Right? And it lets you avoid this problem of opening stuff everywhere and still have code that isn't painful to write in the extreme. Here's another one. Make common errors obvious. So this is actually related to another bromide that people often talk about with respect to errors, which is use exceptions for exceptional conditions. Right? Throw an exception only when there's something really rare that occurs. And that's a good suggestion, but you kind of can't always do it, right? Because whether or not something is a common case depends on context, right? So you, for instance, might have a function for finding something in a list. And in some context, you are sure the damn thing's always going to be there. No problem. And in some contexts, it not being there is completely ordinary. So sometimes it's really an error, and sometimes it's not. And exceptions are a kind of lightweight mechanism for dealing with a case where you really think of the condition as an error. And you want to be able to choose sometimes to use exceptions and sometimes to use explicit passing of returns. And the thing to do in this case is just make it explicit what you're doing. Use conventions, use naming conventions to indicate when errors are coming out in one way and when they're coming out in another. So a thing that we do a lot is we will create signatures that look like this, where we will have, for things that have this kind of error-producing case, we'll often have two versions of the function. And we'll distinguish with them in the name. We'll say there'll be like an ordinary membership function where we check if something is a member, and that will return an option, because sometimes it's there and sometimes it's not. And then we'll also have a version called mem_exn. So that when you call that one, That type is wrong. You can tell I did not compile this. Boom. So that it kind of, but as far as the type is concerned, it always returns just the value, undecorated. But you can tell from the name of the function that if there's an error, you'll see an exception coming out. And this is again, it's a fairly small little kind of piece of hygiene. But it turns out by using this and applying this kind of rule uniformly in lots of different places, you make it easier for people who are reading the code to understand the error behavior of the code. And nobody really likes to think about error behavior, but nobody likes their system crashing either, right? And if you want to write robust code, you need to be able to think about error behavior, and being explicit about the way you're dealing with errors makes it much easier to do so effectively. Here's another one. Avoid boilerplate. So what is boilerplate? Boilerplate is where you have the same code repeated in multiple places. Or really, where you have almost the same code repeated in a bunch of places. Like you have some rough pattern that you put in one place, and then you put it in another, but you kind of change a variable here and change an operation there. And you do this over and over in your code. And to understand why you should avoid boilerplate, it's worth understanding why people do it in the first place. And the reason people do it in the first place is twofold. First of all, there are patterns that they want to do. They want to do something over and over and over again. And there's some structure to how they want it to be done. So they have some kind of cut and paste template that they use in multiple places to do that almost the same thing in multiple spots. And so they want to do something repeatedly, and their language isn't good enough, typically, to encode the kind of what they want to do in a clean way. And this happens a lot if you program in C. Like, if you program in C, C is a wonderful language for a lot of things, and it has much going for it, but it does not have great abstraction capabilities. So there are lots of things, if you want to do them over and over, you need to either program with macros, which has its own set of problems, or you need cut and paste. You need to have boilerplate repeated all over the place. But if you're programming in ML, you basically have no excuse. Like, there are great facilities for abstraction. You should use them, right? Twice is too much. And the reason why it's so important to get rid of boilerplate is twofold. First of all, the structure that you're repeating in multiple places is there for a reason. And remember, your code evolves. Those reasons might change. You might need to change the structure. And you're just not going to remember all the different places where it showed up, right? So you can change some of them when you realize it needs to change, but you're just unlikely to catch them all. And the other thing is, this goes back to reading of code. People have this kind of a human frailty that it's very hard for people to read something carefully if that thing is dull. Like, it turns out, like, you cannot pay people enough to read dull code. Like, I've tried. Like, it's like you cannot convince people. Like, they'll try, they'll work at it. You can tell them it's important, and they'll put in a good effort. But there's something kind of deep in the mind that causes people to kind of skim over the parts that seem dull. And nothing seems duller than boilerplate, because it's just the same thing with two tiny things changed. And yes, it happens to be critical, like whether, when you're doing the calculation on the buy side versus on the sell side, like where you flip the sign turns out to matter a lot. But the fact that it matters a lot does not mean that people will, in fact, successfully pay attention to it. So by writing code that does not have boilerplate, you will do a much better job of writing code that can be read by actual human beings and understood. And it's also just not that hard. Like, it's one of these things where if you just get into the habit, if you just like lower your tolerance for boilerplate to 0, then like you can just do it. Like, you define a little local function, you apply it twice. And interestingly, it's not always less verbose. Sometimes it's a little bit less verbose to just kind of repeat the same pattern over and over, right, if it's not repeated too many times. But the advantage you get by separating it out and not having boilerplate, it's not that it's shorter. It's that the variance in the structure is explicit. You're being explicit about what's the part that's the same and what's the part that's different. And that makes the code flatly easier to understand. Oh, please.
Yeah, because I mean,
Oh.
on the other hand, if you really abstract the hell out of your code, it can be much harder for a reader to figure out that this combination of higher order functions, computes this.
You're leading into my next
Okay.
right. So I agree, and I think one of the things that turns out is that the vast majority of the time, it's easy. Like, sometimes you're right. Sometimes really abstracting everything out requires Herculean efforts. Like, you really have to, like, sometimes you have to build some very complex abstraction. You have to fight the type system because it really wants existential types to get this just right. And there aren't existential types except in this horrible way when you put them in a record. Like, it's terrible. Don't do it. And so this comes to this part. Like, so you guys are just starting out by and large, and so you do not have this problem yet. But if you, right, but great, there we go. But if you come to really like and really use these languages, there is a temptation to spend your time trying to program in the lambda calculus in the sky. Like, you no longer want, like, you get addicted to like trying to like embed these nice static guarantees into your system and make the language take care of it for you, and that will make things better. And like, you are wrong if you think, because it turns out the enemy of good code, the enemy of correctness, is not dynamic guarantees, right? The enemy of correctness is complexity. And sometimes doing really clever things with types or other aspects of the system, sometimes that makes the system more complicated, harder to understand, right? Like, people will good-naturedly, trying to make things better, will look at a piece of code and try and improve it, and they'll end up with something where, like, an experienced ML developer who spent years doing it will look at the types and will be like, I just have no idea what this means, right? And when you've done that, you know you've gone too far. And I think it is a temptation to use these languages more and more because it's fun. It's kind of a game. Like, ooh, I can encode a regular expression matcher in the type system. And like, yes, you can. And no, you shouldn't. Right? In fact, there's a whole like genre of sort of academic work of who I think sort of the apogee is a guy named Oleg Kiselyov, who sort of goes and like shows how like every possible crazy thing that's doable in the type system, exactly how you can do it, and how everything that can be done in one type system can be done in another, and like there's all this insane stuff, and it's beautiful and interesting, and you just don't want to use it. Right? That's sort of and then the other, so I haven't said anything so far about purity, about side effects. Although all the examples of code I gave were examples that didn't have side effects. So again, it's sort of a two-in-one. Like, the first thing is avoiding side effects is good. The vast majority of the time, code that doesn't have side effects, pure data structures are just easier to reason about. But again, like, you shouldn't get puritanical, right? It is not always easier to reason about, and there are cases where side effects are the most natural thing. Sometimes it even makes the code easier to look at and read and reason about, like heretically. Like, it's not always easier to reason about pure code. Sometimes it's easier to read code that has side effects in certain cases, especially when used locally. And there are lots of performance reasons why it makes sense to use side effects for certain kinds of applications. Like, we care about performance a lot. Like, we run automated trading systems that have to be really, really fast and do an enormous amount of volume and read all the market data in the world. And you need to write efficient code. And that means sometimes you have to use side effects. And like, you just shouldn't be that embarrassed about it. The key thing when using a language like ML, it's not to avoid side effects. Because like, avoiding side effects is equivalent to avoiding doing anything useful. Because it turns out, in reality, programs don't just compute things. They do things, right? They send messages, and they write files, and they do all sorts of stuff. And the doing of things is automatically involving side effects. The thing that a language which supports purity gives you is it gives you the ability to, by and large, most of the time, segment out the part that is side effecting to clear and carefully controlled areas of your code. And that makes it much easier to reason about, because it is harder to think about side effecting code, particularly in the presence of concurrency and lots of other issues. And purity is not like, I think it's the wrong approach to try and make everything absolutely pure. You should respect purity. It's a valuable property of your code, but don't overvalue it, and don't kind of tie yourself in ridiculous knots. Like, if in the end you realize you have to write some extremely complicated piece of code to be able to do something in a pure way that's halfway efficient, like, maybe you shouldn't have done it in a pure way. Maybe you should have done it in a side-effecting way. Because again, the enemy is complexity, right? And if you realize that by approaching some ideal that you had, you're forcing yourself to write very complicated code, you're probably making a mistake. All right, so now that I've just given you a haranguing about how one should not engage in excessive type hackery, I'm going to describe some excessive type hackery. So the thing I'm going to describe is a technique that's now, I don't know, a couple of decades old, I think, called phantom types. It has a very sort of fancy sounding name. And phantom types is basically a technique that allows you to kind of coax a little bit of extra proving power out of the kind of ML type system. I mean, in general, when you have one of these type systems, it's kind of proving little simple theorems for you. And it turns out you can kind of add a little extra information at the type level to get the compiler to prove some extra theorems for you. And interestingly, these are really, like, it really is about the compiler proving things to you. Because when it's all said and done, all of these things that we're going to talk about have no effect at runtime. So you can convince yourself about something about your code, but all it does is make sure that the only thing that compiles is code that follows some rules that you want to follow. And then all the information kind of vanishes by the time you get to the actual compiled code. So, and that's why these things are called phantom types, because I mean, there are other kinds of type things that also have this kind of vanishing property, but phantom types are an example that have this property. So I am going to start with kind of the simplest possible example of a type that I want to use phantom types to get some extra guarantees on. And this type is a ref type. So you guys have probably already seen side effects in ML, so I imagine you've already seen refs. And so what I've done here is just create a very simple example of a ref. And because I want to have this all on one slide, I threw the MLI and ML together by kind of writing them in the style where I define the module inline, and I have the sig end to give me the signature, which would normally be in the MLI, and then the struct end gives me the implementation. Right? So the module symbol, it has a type T, and then 3 functions. So this isn't even, we're not even as fancy as having like refs that are polymorphic. They can have different kinds of things. This is a ref that can have one kind of thing, an int ref. So you can create one, and when you create it, you have to give it an integer to start with. And then there's a set function and a get function. The set function allows you to modify what's already in there, and the get function allows you to get the current value out. It's all very simple. But the thing that I want to figure out how to implement now is how to get a read-only version of this ref in a nice way. So in some sense, what we're talking about is also sometimes referred to as capability-style access control, to give it like the fanciest possible computer science-y, actually systems-y name to it. And the idea is I want like another handle to this which has diminished rights. Right? The original handle I have can both read from and write to the thing, and then I want another handle which can only read from. And then I can pass that handle to other places in the code with the confidence that those other places in the code cannot make my copy of it change, but of course I can make their copy change. I can make modifications to my handle, and they will see those changes on their side. So how do I do it? So there's a very straight ahead approach to doing it, which is just to create another module. So again, it's in the same style where I've written the signature and the struct one right after the other. So here, you'll notice that the signature is more constrained. Right? There's a type T, and so this goes back to a kind of standard idiom in ML, which is going to confuse you guys now, which is that, wasn't that other thing type T? Right? Why do we have 2 type T's? And well, they're in different modules, and there's this convention of making the sort of the defining type of a module, calling it T, because you don't really need to give it any other name, because you can tell by context. Right? If you have a module float, it's kind of silly to have float.float. And int.int. It's like it's repeating yourself. So instead, it's float.t, int.t, and in this case, ro ref.t, and the one above is called a ref.t. And to make matters further confusing, in this case, the type t is actually equal in the implementation to ref.t. Right? So what have I done here? I've basically written a new type, a fresh type, except its implementation is the same as the other implementation. The big difference is the interface is more constrained. Right? So in the signature, it says the type T, there's a function called create, which takes a ref.t and gives you back a t, and then another function get, which takes the t and gives you back the contents, the int. And so now it's clear how to get a read-only handle. You take your ref that you had, your read-write ref, you apply ro_ref.create to it, and now you get a read-only reference. Right? And the two cannot be confused now in the program, because the way these signatures are written, the 2 types are considered to be different types. So if you have the read-only handle, even though it's physically equivalent, right, it's the same pointer as the original reference, even though it's exactly the same, the type system will not let you take advantage of that sameness. If you only have the read-only access, the read-only handle, you can only use it to read. You cannot use it to write. Does this part make sense so far? So one question is, so I said before that phantom types would have the property that they would have no effect on the runtime. Right? That when you sort of looked at compile time to what happened, it wouldn't happen anymore. So this is not a phantom type yet. Does anyone have an opinion as to whether or not this has any effect at runtime? Right? Like if I do this, so imagine I have two programs. One is where I just pass the refs around, and I'm careful to, in some cases, not write to it when I'm not supposed to, and I write to it where I want to. Or instead, I use this RO ref to separate out the handles that are supposed to be written to and the ones that are not supposed to be written to. When I run this code in production, do you think it'll be any different? You have this create function where you call create on x, and it gives you back x. So that's the identity function. And then get is actually exactly equal to ref.get. So it does basically go away at runtime. The one thing that might not go away is the create function. There's a question of whether or not the inlining will successfully sort of optimize that away in the compiler. But all you really get out of the difference is there might be like an extra no-op in the code. Right? There might be some kind of operation where it kind of sets something to itself and then does nothing of interest. So it is basically the same. It basically all vanishes at runtime. OK. Oh, sorry. So now we're done, right? Well, we're not quite done, because there's something a little bit ugly about this solution. Right? And the main thing that's ugly about the solution is that the code that you write against this interface, or these two interfaces really, will be less polymorphic than you would like. For instance, I cannot write a function that takes a list of refs, be they read-only or regular, and computes the sum of that list. Like I can't do it because they're considered to be different types. I cannot write polymorphic code that reads, even though they're physically the same, and both kinds of handles both have read access. Right? So anything I'm doing with reading, like I should fundamentally, semantically, there's nothing wrong with having the same code run against both of them. But I can't do it the way this code is written, because the type system has separated out the types and is unwilling to consider them to be the same. And we depend on that for the safety, and we can't kind of get it halfway back the way we've written this code. But we can get it back. Here's how. So now I'm going to hide that example and show you this one. So this pref, P for phantom. And so does anyone look at the type RO and type RW that I have up there? Does anyone notice anything weird about those type declarations? It's an empty data type, right? It's not, or if you want to use sort of fancy-sounding pseudo-mathematical language, it's an uninhabited type. It's a type with no definition. It's an RO. Give me an example. There are no examples. Like it's a type which has a name but nothing in it. Right? So it's a philosophically very deep type. And there are two of them, RO and RW. Right? So we can start to see that there's something weird going on here. So this is where the phantomness starts to creep in. So what we're going to do is we're going to use the RO and the RW as tags to indicate properties of a type. But we're never going to construct one, an actual RO or an actual RW. And we can't construct one, because there ain't no one. Like, there's no definition for them. So here's what we do. So we have this module pref down here, and the implementation is completely dull. Right? There's type alpha t, which is just a ref.t. Well, maybe not completely dull. Alpha t equals ref.t. What's weird about that definition? This is also sort of unusual in a way that you haven't seen before. What's the alpha for? Why is there an alpha? Like, it's not used in the definition. Normally, when you have a type with a parameter, there's a type parameter alpha, then that alpha is used in the definition of the type. Here it's not. And that is the beginning of of the phantomness of the type. This phantom parameter is in the definition, is sort of the name of the type and the structure of the name, but it doesn't actually show up in the definition of what the type means. So that's a little bit weird. And alpha t is just a ref.t. Then we have a create function, which is ref.create. Create, set, and get are completely dull. And then RO of x equals x, another one of these identity functions. Right? The RO doesn't do anything. So there's a little bit of the program that we've written down here in the implementation, but it turns out the real program is being written in the signature. Right? That's where all the action's happening. So we have these three functions, create, set, get, and RO. But you should be skeptical, right? I've called one of them RW and one of them RO, but like it's not clear why one of them allows reading and one of them allows writing. So can someone see from somewhere else in the signature how you can figure out which tag allows reading and which tag allows writing? Yes, exactly. So this value set has this magical, so here we see for set we demand that there be an RW there. And so you see if you do set of an RWT to an int, you can only do it with the RW, right? If you try and pass in an RO, you'll get a type error. It won't let you do it. Now the create function, interestingly, is polymorphic. You give an int and you get, you don't know, it might be read only, it might be read write, the compiler doesn't know yet. And get, again, doesn't know. And importantly, get is polymorphic, right? It could take either kind, which is exactly what we wanted. A read write or a read only can both have can both be accessed using get. And so now we can actually write polymorphic code. And in fact, I'll show you here. We can actually this unlike all the other examples, this really works. Like I can compile this. In fact, I will. So run the compiler. And now, can someone tell me what they think the type of sum should be? And with the magic of our cool Emacs IDE, it tells us it's an alpha pref.tlist to int. So this function is polymorphic. I have now successfully written a polymorphic sum. How about this one? What's this one going to be? Double list. It's going to take a read write, and it has its return value is unit, because it's using list.iter. Read write pref.t list arrow unit. And like note, I did not have to tell the compiler anything. It proved the property on its own. Right? It just sort of used the ordinary type inference. And in fact, I can write a slightly more complicated example over here. So here, I actually let A equal list.map pref.create, 1, 2, 3. Let B equal list.map pref.create, 4, 5, 6. So you might, if you read carefully the interface, think, oh, A and B, those must be of type alpha pref.t, right? Because pref.create returns a polymorphic pref. But if I actually go over here and ask the compiler, it says this one's a read-only, and this one's a read-write. How does it know that? Like all I did was do create. Well, it turns out it learned it later, right? So what happened is, so down here where it says double list of B, well, double list can only take a read-write pref. So right there it learns that the B has to be read-write. And then I stuffed it into this record. And the record over here tells us what the types are, right? It says A has to be read-only, and B has to be read-write. So by stuffing it into the record, I sort of tell the compiler which kind of ref it is. So even though, like, one often sort of has this kind of debased version of how the type inference algorithm in one's head, where it's like you call the function, it returns a particular type, and that's how you know what the type is. But it's not the constructor that tells you. The use can tell you also, right? You can learn things all through the program, and the type inference algorithm is this kind of inference engine that flows the information around until it figures out everything it needs to know. And then, so it's worth noting, A, I learned the type of A in one place, right? That was when I stuffed it into the record. B, I learned in two places. Once when I stuffed into the record, once when I called double list. And those two places were consistent. Everything was happy. I can change the program so that they are now inconsistent. Right? And I can try and compile it, and I will fail. Right? And it will say, boom, whoops. For some reason, it will point to the wrong place in the program. I don't know why. But it will say the right thing, which is, says, oh, it has type RW pref.t, but it's here used with RO pref.t. You tried to use it in one way. It was really being used in it was expected to be the other. Sorry, you fail. Two inconsistent things in your program. It doesn't work. Right? So this is basically the simplest possible example of phantom types. For doing a very simple thing, like you want two different kinds of handles that you can still use polymorphically, you can do considerably more sophisticated things. Right? This is one of these places where you can go off and like take your regular expression engine, embed it in the type system, and prove all sorts of crazy nonsense about your types, and people have done it. But it turns out there are examples like this and a few other fairly modest examples where you can use phantom types in a fairly lightweight way to materially simplify and add nice constraints to your program. And this is one, so you should think of this as a taste of a larger set of things, right? There are phantom types, and there are type indexed values, and there's all sorts of cool stuff you can do with macros to do type generic programming. There's a lot of cool stuff in ML that you can learn after you get out of the first steps. And a lot of the time when you sort of see stumbling blocks in front of you in using ML, part of it is you just need to learn some more patterns, some more ideas about how to actually write effective programs. And you can get really far without getting this fancy, but at a certain level, it starts being worthwhile to learn some of these techniques. OK, so I think I'm going to stop now talking and see if you guys have any questions, either about this stuff in particular that I've talked about, or sort of more generally about like what it is like going off and using a crazy minority language in the real world. Modules are a great sort of building block for building big systems. They work really well. And the kind of abstraction you get out of modules is in many ways kind of substantively better than the abstraction you get out of objects, because the object abstraction is usually and most naturally about one thing. But sometimes you want abstraction that's about a bunch of things and how they relate together. Sometimes things are the same type, sometimes things of different types. And modules are kind of a more natural way of doing that. And modules and sometimes functors and often parametric polymorphism and higher order functions are very good ways of factoring out your system and building really large scale systems. I mean, when I say really large scale, we have somewhere between 1 and 2 million lines of code, which is very, very big for an ML code base, probably the biggest in the world, and is, I think VI with all its extensions is about 1 million lines. So, we're a little bit past the standard Vim actually. VI is much smaller. So it's a sort of moderate, it's nothing like the code bases you see at a really big company, but it's a sort of reasonably sized code base. So we have some experience of operating at scale. But when you're building, one of the things I think people often forget about is when you're building a big complicated code base, when you do it in C, you often have to add abstractions anyway because you can't actually get things done otherwise. Like, go look at like the implementation of GTK, right? There's a big ass library, right? And they have like their own like special G object and all these, like they have layers of cruft to get this stuff. And they have to do memory management because for a really big code base, for if you're doing really complicated stuff, the memory management requires some automated techniques in addition to kind of just manually tracking things. And that stuff costs. Programs written in C also spend time garbage collecting. It's just that the programmer also spent time writing the garbage collector. And it's probably not written very well. So the difference between those two is not as big as you might think. Now, for some things, you have to drop down to C, right? You do that sometimes. There's nothing embarrassing about it, just like there's nothing embarrassing about using mutable state. But you can write the vast majority of your code in OCaml and basically be fine. There are places where ML is worse. So one place is, like, nobody uses it. So there aren't as many libraries. And when you want to use some external library, like you have to write the binding to it yourself. And if I was doing web programming for a living, I would not use OCaml. Like the libraries aren't good enough, they're not well developed enough. Like I'd go and program in Ruby or something, God knows what. Like I would not program in OCaml. There's a lot of work to be done on the library level, and you're just giving that up, right? So for the kind of things we're doing, like they turn out to be sufficiently bespoke that ability to access external libraries isn't as big of a deal. I think the libraries for doing UI work in OCaml are not good. Right, that's like writing GUIs in OCaml is not pleasant. There are no great libraries doing, no good cross-platform ways of doing it. Like to give you a sense of the low levels to which we have sunk, we write many of our UIs in curses. Curses, right? A technology so crufty that many of you don't even know what it is. It's like imagine like the super advanced green screen applications, like an old like IBM like mainframe 1970s text on a screen, except with colors. So it's slightly less horrible. So the UI stuff is not great. Another thing which I was thinking of talking about but didn't get to cover is that certain kinds of generic type kind of things like writing a printer, something that like prints out a value in a clean way, is a little bit more painful in ML. And to really do it well, you need to do some fancy tricks by using, there's various ways of doing it. We do it by using the macro system to write things like code for automatically taking types and serializing them out and loading them back in, and things like that. Some So I'd say that's basically, there are certain library issues, UIs in particular, and certain kinds of things like writing generic printers is a little more painful. But those, I think, to a large degree, we've solved, and so haven't really been a pressing problem for us.